Yeah, so my talk is called Learning Neural Networks with Quantum Computers and also Learning Quantum States with Graphical Models. So it's two topics. Thanks for the invitation, and it's awesome to be here. I'm a PI at NUS and the Center for Quantum Technologies. So I will talk about essentially two topics, our paper on the Quantum Alphatron, and this is sort of using a quantum computer for a learning problem. And then the second topic is tomography or learning quantum states using using algorithms for graphical models. So I mean, machine learning, everybody by now knows everything about it. You know, due to ChatGPT, and here, as you can see, that the number of users has grown like tremendously and so on. And I let it write a poem on quantum finance, a topic that is not familiar to everyone. But it came up with quite a nice poem there. A computing power that warms and portfolios optimized with qubits might. So that's kind of cute. Another thing, like you can generate pictures like here, like I typed in something like economist and magical, and this is what came out. Anyway, into DALL-E. So in terms of quantum machine learning, this figure is very old. It's about the intersection of quantum information processing and machine learning, and it sort of goes both ways, right? So you can have both using quantum computers to enhance machine learning problems, but also using classical machine learning for sort of learning about quantum systems or designing quantum experiments. So sort of like the understanding of QML, there's this sort of maybe a separation between sort of heuristic methods and theory. And of course, people want to get these things closer together. So on the heuristic sides in classical ML, we have these large-scale neural networks that consume a lot of hardware, a lot of data, billions of parameters. But there's no sort of guarantees that they work. They do work in practice really well, but there's no or increasing understanding why they work, but maybe not like a deep understanding. I don't know. From the theory side, computational learning theory tries to sort of formalize many of these things. So they pose well-defined learning problems. They have algorithms with provable learning guarantees, and they analyze sort of sample complexity and runtime. And the same, I would say, there's the same sort of separation as in quantum machine learning. So where many people discuss variational methods or quantum neural networks for solving problems. So on existing hardware, for example, these are sort of heuristic methods. Often you have small data input in this case, because every qubit, for example, gets, let's say, one data point or something. So some methods are like kernel methods or hybrid quantum classical methods. These are some of the common things that were discussed. Here, you often, as far as I know, you get no provable advantage, as far as I know, at this point. It sort of like opens, there's a field of, let's say I would call it quantum computational learning theory, where we also have well-defined learning problems. We get the data from maybe a QRAM or somewhere, and we analyze sample complexity and also quantum advantage. So this is the first project is the Quantum Alphatron. That's joint work with Miklos Santa, Nai Shugur, who's my student, and Si Yang, who was a student at CQT. So this is, again, in the classical machine learning, it's a fundamental challenge to find provably efficient algorithms for learning neural networks from samples. As a worst-case result, even learning a single ReLU function is hard here in this agnostic learning setting. So then you can maybe put more restrictive assumptions on the problem, and you can hope for polynomial sample complexity and runtime. So the Alphatron is one of these algorithms that can learn a two-layer neural network in polynomial time. And it's doing this by learning a kernelized, a noisy general linear model. So this was published by Gül and Clevans in called the Conference on Learning Theory. So here, just as a motivation also about learning two-layer neural networks, it's essentially the input-output. You have samples X, you have data X, and you're producing sort of an output Y. And the two layers you have your weights where you map the inputs to the weights to the neurons, and then you then linearly combine all the neurons with another vector B. So they have two layers. And since this inside here, we can actually approximate by a polynomial, and hence we can write it like this using a multinomial feature map and some vector V and plus some noise. So that's why sort of the Alphatron can learn this. So I'm already jumping ahead a little bit.
Sorry, can I just understand the setting properly? You're in the agnostic setting, where there's
no, we're not in the agnostic setting.
So like the data is guaranteed to come from a neural network.
Yes.
But you're not going to output a neural network.
We output this the hypothesis, essentially this V, this one.
So it's improper in that sense.
Yes. I define it in the next slide. Okay, so quantumly, I mean, the motivation is similar. It's like kernel methods have been extensively discussed in the quantum community. They haven't shown any kind of provable advantage. So for example, here the paper from IBM that was published in Nature. So it's interesting to study provable algorithms, quantum algorithms that in this kernelized setting. And we want to also avoid dequantization, so classical algorithms that are better than any quantum algorithm we design. So then the question we're asking is sort of using quantum data input, sort of like a QRAM and some quantum subroutines, can we obtain an advantage for the Alphatron? So what is the learning setting? It's not agnostic learning, it's this probabilistic concept learning due to Kearns and Shapira, a pretty old setting. So here, the general is like you have a feature domain, you have labels 0, 1. You have a concept class of functions. How does this concept class enter? This is mapping the feature domain to some output 0, 1, in between 0, 1. So you get samples from a distribution. The constraint on the distribution is that your conditional expectation value of y given x is an element of the concept class. So the interpretation is for each x from the domain, C of x is sort of the probability that x has label 1. Right? So now, and then we want to minimize some figure of merit, say some expected square loss. So to actually now define a specific concept class, so this is what Girl and Cleavance did for solving the neural network problem. So you have a domain, the unit ball in n dimensions, and 0, 1. So this is x and y. A concept class. So now this is the definition of the concept class. So you have a Lipschitz function. You think of it as your sigmoid. You have a feature map that maps from the unit ball to some higher dimensional vector space, ND dimensional. It has to be bounded in 2 norm. You have an unknown vector v, where you only know that is bounded, the 2 norm is bounded by b. You have a bounded noise function in some interval, minus zeta plus zeta. And it has a constraint that the second moment of this is bounded by epsilon 0. So now we're getting samples from a distribution where this conditional expectation value is our Lipschitz function, and then the inner product between v and our feature map, plus some noise term, right? So C is an element of the concept class. So the problem is, given samples, output a hypothesis H such that this is satisfied. So this is a generalization bound with expected value over the distribution of the square loss is smaller than epsilon. So there's a lot of constants and so on, but this is, I mean, what you have to do to get to a provable result. And this output I want to achieve in sample complexity and running time polynomial in the dimension of the feature space and 1 over epsilon. So in addition, I mean, again, this psi is actually the multinomial feature map. So you're mapping x to all the monomials. You use like x1, x2, x1, x3, and so on. And so this defines a kernel between different x's that is given by this polynomial kernel. So again, the Alphatron tries to solve this problem. And in high level, intuitively, it does it. So you're getting samples from the distribution. Starting with some vector, say the all zero vector, you make an ansatz that your sort of hypothesis vector is a linear combination of the training data of the as an input into your feature map. So linear combination of that. And this is as you give as a hypothesis. And then, so we now, the problem is sort of transformed into just optimizing those alphas. Does it make sense? So the Alphatron is a gradient descent-like algorithm for optimizing alpha. So I show it in the next slide. So this is, so we have your training data. Also, we have some testing data. So M1 is the training, and M2 is the test data. We have our Lipschitz function. We have a number of iterations t, a degree of the multinomial kernel, and a learning rate lambda. We start with the all zero vector, and then do t steps of defining a new hypothesis. It's given, as I said before, with our ansatz. And we then, with a gradient descent method, optimize the alpha. So the new alpha is the old alpha plus the learning rate, and then the difference of the label and what the hypothesis tells us the label is.
Okay.
Yeah?
So it's just a kernel method that you optimize with gradient descent.
You could say that this is it. Yeah.
I'm a bit you probably say why, but like I'm a bit surprised to change from the normal kernel method to gradient descent, which makes everything less provable and more difficult. So is there a reason?
No, I think the algorithm is easy. The cool part about this paper is that it defines a class of problems that provably it can solve.
But you need the gradient descent switch for this proof, which seems like
it appears. I mean, you need this. There's other works that have other concept classes that, for example, rely on multiplicative weight updates. So, for example, if you have some L1 constraints, you actually get an algorithm that has multiplicative weight updates. So this is called the sparsitron. It's another provable learning algorithm. But here, turns out, that the gradient descent works. Okay, so in terms of the runtime, so with a quantum computer, we may be able to improve the runtime of this algorithm. So where can we start? Yeah.
So in order to get guarantees about how long it will take this algorithm to be able to learn a concept, what promises do you have to make on how the learning rate is set?
Yeah, so it will come. So this algorithm has no guarantee. Like it can, t is just a parameter that I'm giving it. So later on, to get the learning guarantee, we will set all this. The learning, yes.
Okay.
So, but for the runtime, for now, it doesn't actually affect us. If we want to discuss the runtime, okay, I just discuss it as a function of t and lambda and so on, right? Okay, so what are the computationally hard steps? It's like evaluating the kernel here. And so when I define a new hypothesis, I have to evaluate the kernel, and I have to evaluate this sum. So, and we can hope maybe we get a speed up for both. So maybe let's briefly discuss the runtime here. So I'm having t steps. I do this kernel evaluation, which costs me n, because I'm in the feature space. I'm basically have to compute this inner product here. And I have to compute m square different. So let's see. So I think there's some m square here. I've forgotten it now. So there's, so m square. What is the m square? Oh yeah, here, right? Anyway, I will maybe later.
Patrick,
yes.
Just out of curiosity, are you also comparing against randomized algorithms for computing inner products?
Yes. So this comes in. You're predicting my talk. Yes. So So then, what are some quantum tools we have available? So we can assume that we have quantum access to our training data. So we have for each feature, we get the corresponding training, the corresponding entry in our training set. And then we use things like norm estimation for computing inner products and so on, and the kernel. So like these two theorems are just examples of theorems. This theorem is just an example of a theorem we're using. There's other versions of this that we're also using. I'm not listing all of them. Also, we're assuming that we can dynamically update this QRAM in linear time. So if we can store our alpha vector in a quantum access like this. Okay, so what we're doing is like to get to a quantum version of the Alphatron. So remember, our original runtime is Tm squared times n. The first trivial sort of step is, so we have our kernel computation and that summation that we do inside the loop over T and M. Now we move the kernel computation just to the beginning. As a trivial sort of step, we compute all the kernel matrix essentially in the beginning. So this then changes the runtime to m squared n, and then for the kernel computation, and Tm squared for the main loop. So that's a small improvement over here. So then what we can do is essentially what Nathan was suggesting is to, instead of computing the inner products exactly, we're computing them by sampling. So we're constructing a sampling data structure here in linear time, and then computing the sum by sampling. So this improves. So the same we can do for the kernel. We're constructing a sampling data structure for our training data, and then computing the kernel approximately. So now, if we have an epsilon for the kernel, for each entry of the kernel matrix, this is epsilon k, then this step will cost mn plus m squared over epsilon k squared. So this is the preparation of the data structure, and then this is m squared, the size of my kernel matrix, right? And for each entry, I do something like 1 over epsilon squared. And similar for the summation, I have a loop of Tm, and then I compute these inner products inside there. And then to get to the quantum version, I assume that I have my quantum query access to my training data. I produce the same output that my approximated algorithm is producing, and then same. So here in the inside loop, I also have a quantum RAM where I store my alpha vector, and I can import and sample from the alpha vector. I can prepare a quantum state as a superposition of the entries of alpha. So, and that I can use then to compute the sum approximately to the same accuracy, but quadratically faster than the classical algorithm.
Can you explain why the MN scaling is worse for the kernel method than it is the classical approximated one?
So
the epsilon scaling is clearly better.
Here, right?
Yeah.
This one is better, right?
No, it's not.
So yeah, sure. Here.
Because it's not. There are some asymptotically where that's worse.
I'm preparing a sampling data structure for each training vector. This costs me. So I have m training vector of size n. So I'm preparing a sampling data structure for each of them. So that's this cost, which I don't do here. I only have query access to it. I don't have sampling access here. So I don't get this. I don't pay this price.
But you agree see why it's worse, right? In some limits, because it's multiplicative, not additive.
Yeah, it's multiplicative. Yes.
So I was just wondering.
So I'm not saying that this one is better. This is just an intermediate step. For us, we're not claiming that this is better than even here, this one, or we're not claiming that this is better.
Okay.
We're using this to prove the correctness of this algorithm, which then applies also to this algorithm.
I see. Okay.
So in the end, I'm comparing only this algorithm to, let's say, this algorithm, right? This approximate is just an intermediate step for proving the correctness, that it's actually okay to get to use an estimated kernel matrix instead of the exact kernel matrix, and so on. Okay, I'm summarizing. I don't go into more detail than that. So the kernel matrix is estimated by using query access to the data. The approximated algorithm is storing the alpha in a sampling data structure in linear time and then approximate by importance sampling. The quantum one is storing this sampling data structure in a QRAM in linear time and estimates the sum via importance sampling assisted inner product estimation. So, I mean, maybe some people, experts, they know this KP data structure. So this we're embedding into the QRAM. So as I said, the convergence for the approximated algorithm can be proved, and it applies then to the quantum as well. Okay, so to get to the results, what's my time? So recall sort of some definitions of our concept classes. We have an unknown vector v in a high-dimensional space that has some bound b. We have a bounded noise function, and we have our concept class of functions like this, right? And we want to output an hypothesis, and here we cannot do better than this, but this is our task. We want to output an hypothesis, some constant times square root of epsilon 0. Epsilon 0 is given here by the bound on the second moment of this noise function. So this is intrinsically, we cannot get better than epsilon 0. So now we plug in some numbers, and this is the original paper already did this in some sense, but we just show that under these estimations, it can still work. So the number of, So the number t is depends on b, zeta is the bound on the noise function, and epsilon 0. And m is the number of training examples, so the sample complexity. And epsilon for the inner products has to be something like square root of epsilon 0 from the concept class. And then we can show that for the main loop, and here I don't show the kernel part, but the main loop part has this improvement. So we, from a runtime of b zeta to the 10, so zeta here, to the 10, epsilon 0 to the 5, we're getting an improvement not in b, so b square, but zeta to the 8 and epsilon to the 4.5. This holds in this regime. If this doesn't hold, then there's no improvement. So it's a small speed up while returning the learning guarantee. This is all we were able to squeeze out from here. And so to conclude this part, it's a bit similar to other papers that came out around the same time when we started this on L2 margin SVM classification, zero-sum games, semi-definite programming, also the sparsitron from us. So here, as an example, we have the algorithm for zero-sum games that classically is an old paper, a nice paper, runs in n over epsilon square, and the quantum algorithm was shown to run in square root n over epsilon cube. This is the paper from 2019. Since then, it has been improved to epsilon to the 2.5 by using a different data structure. So maybe ours can also be improved, but yeah, let's see. So again, to summarize the quantum alphatron, we make strong input assumptions. So we're given our data in sort of this query access. Also dynamically, we use a QRAM. So we store data and then use it. It's a well-defined learning problem. We get a small but provable speedup, and it preserves the learning guarantee of the original algorithm. So that concludes the first part.
I guess one question that I wanted to get is for the quantum input coming in. Mm-hmm. If you're getting the one over epsilon things, that's usually implying that you've got coherent access, as in you've got a unitary that can effectively prepare your input, right?
So we have this query access here.
Right. So my question is then, in this case, is it kind of like a fair comparison to what you would end up seeing in the classical world? Because in the classical world, right, we don't kind of have, if we were thinking about classical probabilistic data coming in, then we wouldn't have that type of an access. We would just have access to individual states that we couldn't unprepare.
So here, I mean, here you have all the training data. Yeah? It's given to you. This is the classical algorithm.
What I'm saying is, like, imagine your training data is provided to you classically as a probability distribution, not as a bit string. Right? Then in that case, the unpreparation assumption wouldn't be appropriate.
I think you're right, yeah, and I think your question goes a little bit in towards online algorithms.
That's
right?
exactly kind of what I'm thinking.
When you're given your data as you go along, and indeed in the quantum setting, the analogous setting for me is given the oracle. You're given different oracles as you go along. So I don't know if this answers your question, but
sure, it's fair.
Yeah.
I guess Oh, sorry. No, go ahead.
So did you ever mention why this algorithm can't be dequantized?
So in some sense, at least I don't know if we did the perfect way of, but we dequantized it first ourselves. Like this one is the dequantized. This is using all the Ewen-Tangs techniques to dequantize. Right. So that's why we're only getting a small speedup, right? Because in the dequantized results, you're already assuming that you have an L2 sampling data structure, right?
So did you at any point have to assume that you have L2 sampling data structure?
No, we're constructing it on the fly.
Oh, okay.
We only assume query access from the beginning, and then if we need sampling access, we're constructing it on the fly. And that costs linear time, right? At least, I mean, n log n or something. Anyway, there was somebody else? No? No, okay. So now changing sort of direction, going away from quantum computing and towards analyzing quantum data. So this enters sort of the minefield of quantum tomography. I guess the previous one was also a minefield, but yeah. So this is our paper, Provable Learning of Quantum States with Graphical Models. It's joint work with Li Ming, who was a postdoc at CQT, Naishu, and also Professor Lu from China. Okay, so first motivation is quantum tomography. So given multiple copies of a quantum state, of an n-qubit quantum state, can I learn it? And of course, it depends on the metric and so on. So the latest and greatest results are these from O'Donnell and Wright and this other paper. For mixed states, you need d square over delta square, so where delta is your trace distance. For pure states, you can, in 1 minus the fidelity, you can do in d over epsilon. So output a state that is close to the true state. But then can we do, so this is exponential in the number of qubits. So can we do better? So there's some interesting results, of course, some older results on learning stabilizer states. So if we, that we can do in linear sample complexity and n-cube time complexity. This is a result by Aronson and Gottesman. Also, Gibbs states, matrix product states have been discussed. We can also consider a weaker sense of learning, say like older papers by Aronson on pretty good tomography, later paper on shadow tomography and classical shadows. So where we maybe are interested in how does a quantum state predicting many properties from very few measurements. So yeah. So there's an interesting survey by Anshu Anurag and Aruna Chalam. So another motivation for us is these famous or interesting works on neural network quantum states. I think it started with Kaleo and Troyer, a science paper from 2016. They give a variational expression for the wave function of a quantum many-body system where the ansatz is a restricted Boltzmann machine. So where you marginalize over the hidden nodes. There's a well-known theorem that any probability distribution can be arbitrarily well approximated by an exponentially sized restricted Boltzmann machine. by the marginal of that. And the corollary to that by Huang and Moore is any quantum state can be arbitrarily well approximated by such a neural network quantum state based on an exponentially large restricted Boltzmann machine with complex parameters. So this is another motivation for us for our work. And then also the existence of provable learning methods for graphical models. So we've seen already the Alphatron that can learn a 2-layer neural network. There's the sparsitron that can provably learn an Ising model, so you get samples from the Ising model. And then there exist nice results on learning RBMs when you get samples from the visible layer. And this is based on a greedy structure learning algorithm from Bressler, Köhler, and Moitra. So this is I cannot give them enough credit, so a lot of the next slides are based on this paper, and we extend it in a small direction. So our idea is sort of a combination of two things I mentioned already, so the provable learning methods and neural network quantum states, but we add sort of a robustness proof of these provable learning methods to it. So what do I mean by robustness in some sense? So this is our key idea, is looking at the literature, instead of given samples from the true distribution, maybe there's an RBM or something, I'm being given samples from a contaminated distribution. And this is sometimes called Huber contamination. So here, this is the precise statement of what Huber contamination is. I'm given samples from P of epsilon instead of P star. But I still want to learn P star. And so the key idea is let our quantum state be some neural network quantum state that is corrupted by something that's non-neural network quantum state. So we have some state that is an RBM state, and we have some corruption there. Yes? I will define it, yeah. Yes. So what epsilon can we tolerate? That's basically the question, the technical question. So what we do is, so this is an overview of the work. So we have been given multiple copies of a state psi that is close in some measure. So in our case, it's the LP distance to some neural network quantum state. Then we measure our state psi. We get bit strings. We measure on the computational basis. And then from the data, we learn the structure of the RBM, of this RBM. Yes, please.
You mentioned these tomography results earlier for the pure states, like this HHJ plus 17
yes.
result that shows that with D over epsilon sample complexity you can learn pure states.
Yes.
But that is making use of entangling or tangled measurements.
Yes,
right?
so joint measurements.
In the joint measurements.
Yes.
Otherwise, that's not.
I think the best result, I forgot it. Like it was also in. So let's see. What's the one where you don't need? It's D cube, I think.
Yeah.
D cube over. That's when you don't have this. When you only measure a single state.
Exactly. But that's my point.
So like this.
Your setting, because it seems to allude to having non-entangled measurements. So what are your measurements?
Yeah. So we don't entangle anything.
Okay. So
we're just measuring each of them on its own. So using entanglement, I mean that could be another.
Yeah. Okay.
I mentioned it as a future direction.
That's my question.
Can I ask another question?
Yes.
So you have this noise model that you somehow think you don't have the state correctly, right?
Yes.
Shouldn't you then also assume that in the different copies, they are not really different copies, but only close to?
I think we can allow,
Because conceptually, if
all of the, they don't have to be the same. They can be, around, but as long as they are epsilon p close. Yes. So from the data, we want to extract information about the restricted Boltzmann machine that is this phi r state. So to do this, it's actually an interesting strategy. Is first to learn structure of what nodes in your restricted Boltzmann machine, what nodes of the visible layer are connected at all. You do this to reduce the number of parameters you have to learn then if you want to do full state tomography, right? When you know the structure first, the number of parameters is reduced. And then, using the knowledge about the structure, I will define everything. We can then find a state psi star that is epsilon t close to the true psi. And there is actually polynomial sample complexity. Okay, so okay, I'm nearing to the end. So what's a neural network? In our case, what's a neural network quantum state is this definition. So we have some quantum state where with positive amplitudes, no complex part, where P of x is the marginal distribution of a restricted Boltzmann machine. If you want to have complex part, there's some work to extend this with another restricted Boltzmann machine or with complex parameters of the RBM.
So to compute this precisely, you'd have to compute the partition function of the for the RBM. Mm-hmm. So my question is, under what circumstances do you assume psi RBM can be precisely prepared?
So we're not assuming that this can be prepared. No, we're getting a psi that is close to this.
Okay, cool.
That's the key idea. Yeah.
Another quick question.
Yes.
So in the previous slide, you had sort of like this renormalization of the graph structure. What do you do with this graph once you've sort of simplified it?
I will mention it later, yes. So you know which, so in the end, what this is underlying, this is learning a polynomial. And you're learning the coefficients of a polynomial. And this tells you what monomials are important in the polynomial and what you don't even have to learn. So this reduces the number of coefficients you have to learn. I think this was also used in the recent paper by Moitra on learning arbitrary Gibbs states, quantum Gibbs states. Anyway, so this kind of structure learning idea. Okay, so this is a very important idea, I would say, for this field. But it's not our idea. So I said I give plenty of credit to these people, right? So, okay. Ours is making this robust. Okay, so samples measure in this state, measure in the computational basis of psi, not phi. Sorry, not this state, but the close one. Yeah, so what states do we allow? So again, the definition of a restricted Boltzmann machine is the following. We have two sets of variables, visible ones and hidden ones. So we have n visible ones and m hidden ones. It's a graphical model with a joint distribution. That is this Ising model, but you have only connections between the hidden and the visible, not among them. So I have a weight matrix J and some local fields H and G. So then we are restricting, these are many RBMs, so we're restricting to ferromagnetic RBMs where all the couplings are positive. All the fields are also, local fields are also positive. And
is that done just to make it frustration free?
Pretty much to make the learning easier. Otherwise, you cannot learn it efficiently. Yeah. This is very hard restriction, but this one is a bit more loose. So this contains ferromagnetic RBMs. These are called locally consistent RBMs, where these couplings here they have to be positive, but here they can be for each hidden node they can have to be the same sign, but between different hidden nodes they have different signs. And for these two RBMs. Provable learning methods have been shown. So to make it even nicer is to define alpha beta non-degenerate RBMs. Essentially, this alpha beta are two parameters. One is if a coupling is non-zero, it has to be at least alpha. So this allows that you can identify the couplings. And then beta is sort of a parameter that it's like an inverse temperature that tells you about the general scale of your state. So this is here you can see the sum over the columns and the rows of the coupling matrix. So now these are neural network quantum states that are like the previous slides. So they exist in alpha, beta non-degenerate ferromagnetic or locally consistent RBM. This I will define later, the 2-hop degree. And they're given exactly like this, right? So for this class, this algorithm can directly be applied. For the locally consistent, there's another paper, but for this class, the algorithm can directly be applied. Now we define closeness to this class of RBMs, neural network quantum states. So this is so we have this measure of closeness. One can debate that. So if you have two quantum states with amplitudes psi and phi, we absolute square them and then compute the LP distance of the probabilities. This, of course, gets rid of all the complex. This, of course, gets rid of some things that you may be interested in. So now then we define a class of epsilon closed states. Is that for each state in the class, there exists a neural network quantum states that's epsilon p close in LP distance. And so note that this state can have complex amplitudes, right? So our general setting. So I think we're running. Yeah. Anyway, we have some time. So what is learning RBMs? So you're marginalizing this joint distribution. And so what you're getting is the marginal distribution P of X, so no more Y, is some, actually it's a Markov random field. So that's a well-known and very interesting fact about marginalizing over RBMs. So many RBMs can lead to the same Markov random field. So we cannot expect from the visible layer, we cannot expect to actually learn J. So this example, for example, if you do the marginal version of this, you can see that these two are independent. So this cannot be distinguished from a model where you have just two visible nodes that are independent. But we can hope to learn this potential f of x. That depends on our parameters. In particular, we learn the structure, so what monomials show up in F, and the coefficients of a Fourier expansion of this potential. And for that, we use structure learning to reduce the number of coefficients we have to do. Okay, so what does structure here mean is actually, what helps us is to know the 2-hop neighborhood of each visible node. So the graph theoretical 2-hop neighborhood will be just you have two jumps, and you're going from, let's say, 1 to 2. So this would be in the graph theoretical 2-hop neighborhood. In the 2-hop neighborhood we're talking about is more about independence. So if I condition on x2 then if x2 is in the 2-hop neighborhood, then so if I condition on the whole 2-hop neighborhood, then the rest of the visible nodes don't influence my visible node anymore. So here's the precise definition. It's the smallest set such that xi conditioned on the set is independent of all the other xj's. Okay? It's a bit difficult, but so then we have a 2-hop degree that shows up in all the results. Is the maximum size of the 2-hop neighborhood. So it's a fact that this 2-hop neighborhood definition is actually a subset equal of the graph theoretical 2-hop neighborhood. So you can see this from here. The graph theoretical would be two jumps, let's say this, but actually here, because they're independent, actually the 2-hop neighborhood of V1 is empty. So the question that the original paper is asking is, can we find N2 from samples? And they do this by looking at how different variables influence each other. So they have this influence function. So if I so this is a set function. So given a set S of visible nodes, I compute the expected conditional expectation value of I with respect when I set all these nodes to +1. So and then I see how much do they affect my xi. So a key property of this is that it's a submodular set function, monotone set function. So we define a noisy version of that. So here, for this computing the expected value, you use the probability measure the RBM, we say we define a noisy version where you use a p tilde, compute the expectation value. So this is my I tilde. And then we show a simple lemma that if the total variation distance between p and p tilde is smaller than epsilon1, then also these two influence functions are not too far away. And then since we are learning from samples and we don't have access to the distribution p, we also define the empirical version of that. So where you compute the expectation value from the samples. So then from the original paper, the only modifications that we're using the noisy version of the influence function is that, so we're getting samples from the quantum state psi, and then we're sort of greedily finding the set that is the 2-hop neighborhood. So here there's a maximization, it's a bit difficult in the short time to explain, but so we find an influence maximizer, add this maximizer to the set, and then we prune the sets by identifying the significant neighbors. So it's a little bit tricky but yeah. And so it can be shown that this is correct if the number of samples is 2 to the d2 log n over eta, where eta is given by alpha, a function of alpha and beta. These are, remember the alpha beta non-degeneracy. And we do this for k steps, where k is given by d2 log, 1 over eta. So then the statement is that we can, given some epsilon1, let us be given many copies of psi in that class where phi r is the corresponding neural network quantum state with distance epsilon1. If epsilon1 is smaller than some threshold, then the 2-hop neighborhood associated with the state phi can be learned from samples of psi with only log n samples of psi and time complexity of n square, about up to log factors. And I'm removing all the other, I'm not quoting all the other dependencies on alpha, beta, d2. That's why informal. And so the threshold that epsilon1 has to satisfy is this one. In particular, it's independent of, so it doesn't depend on the dimension, yes. Yes. So now I just have 2 more slides, I think. It's about full state learning. Now we know the structure, we can hope to learn the potential that approximates our state. So by the structure learning, we've reduced the number of coefficients that we have. And so this is the reduction. So if you didn't do the structure learning, you would have something like n to the d2 coefficients. Now we have only n2 to the d2. So it's still a strong dependence on d2, but it's linear in n. Remember, that's the number of visible nodes. And so one key feature that the previous paper didn't have to do, because they didn't have the corrupted data, so they can now just apply some so-called GLM-tron to learn the coefficients. We have to, because we're learning with noise, so we have to actually use the Alphatron for learning the coefficients of this polynomial. So there's a lot of technical details that one has to do to be able to do that, but that's the key idea here. And so then we can arrive at this following statement. So let us be given many copies of psi, which is epsilon1 close to some neural network quantum state phi r. And its magnitudes of the amplitudes are p tilde. So then let another epsilon parameter, total variation, this is our target epsilon that we want to learn. If the number of copies is 2 to the d n square over epsilon tv to the 4, and epsilon1 is below a threshold, then we can find a set of parameters that represent I think this should be a no star here. We can find a set of parameters, p star, that represent this p. such that this guarantee holds. So in total variation distance, we have this guarantee, TV. And so the sample complexity is n square. So remember, this is the number of qubits, right? N square over epsilon TV to the 4th. And the threshold depends on 1 over n square here, and also TV and epsilon TV to the d. So in general, because the d2 shows up exponentially, we think about d2 to be log n. So this is our guarantee that we can. And so a little bit discussion is some open directions, is to extend this to where your neural network quantum states already has complex amplitudes. Then in analogy to, I think what was mentioned before also, that we could perform some joint measurement or some unitary before we do the measurement, similar to, for example, the shadow tomography. We can study other distance metrics. We have a class of quantum states that we can efficiently learn now. We can study that class more. So we can, for example, study the circuit complexity of that class of states, or the connection to other works that have been done by some of the people here in the audience. And we also can study the connection to matrix product states. Okay, so I showed you 2 aspects of quantum machine learning. One is the quantum accelerated machine learning, where we quantized a provable machine learning algorithm. It's less relevant practically. I mean, so this algorithm is probably, or the guarantee is not necessary for any practical problem, but it is of theoretical interest. And then, so methods from provable graphical model, or RBM learning in particular, may find application in quantum state tomography. That's the gist of the second part of the talk. Okay, thank you for your attention.